The Minkovski diagram, also known as a spacetime diagram, was developed in 1908 by Hermann Minkowski and provides an illustration of the properties of space and time in the special theory of relativity. It allows a qualitative understanding of the corresponding phenomena like time dilation and length contraction without mathematical equations. The term Minkovski diagram is used in both a generic and particular sense. In general, a Minkovski diagram is a graphic depiction of a portion of Minkowski space, often where space has been curtailed to a single dimension. These two-dimensional diagrams portray world lines as curves in a plane that correspond to motion along the spatial axis. The vertical axis is usually temporal, and the units of measurement are taken such that the light cone at an event consists of the lines of slope plus or minus 1 through that event. A particular Minkowski diagram illustrates the result of a Lorentz transformation. The horizontal corresponds to the usual notion of simultaneous events for a stationary observer at the origin. The Lorentz transformation relates to inertial frames of reference, where an observer makes a change of velocity at the event. The new time axis of the observer forms an angle alpha with the previous time axis, with alpha less than pi 4. After the Lorentz transformation, the new simultaneous events lie on a line inclined by alpha to the previous line of simultaneity. Whatever the magnitude of alpha, the line T equals x forms the universal bisector. Basics. For simplification in Minkowski diagrams, usually only events in a universe of one space dimension and one time dimension are considered. Unlike common distance time diagrams, the distance will be displayed on the horizontal axis and the time on the vertical axis. In this manner, the events happening in the one dimension of space can be transferred easily to a horizontal line in the diagram. Objects plotted on the diagram can be thought of as moving from bottom to top as time passes. In this way, each object, like an observer or a vehicle, follows in the diagram a certain curve which is called its world line. Each point in the diagram represents a certain position in space and time. Such a position is called an event whether or not anything happens at that position. The space and time units of measurement on the axis may, for example, be taken as one of the following pairs: units of 30 cm length and nanoseconds, or astronomical units and intervals of 8 minutes and 20 seconds, or light years and years. Path time diagram in Newtonian physics. The black axes labeled x and caught on the adjoining diagram are the coordinate system of an observer, which we will refer to as at rest, and who is positioned at x equals 0. His world line is identical with the time axis. Each parallel line to this axis would correspond also to an object at rest but at another position. The blue line, however, describes an object moving with constant speed v to the right, such as a moving observer. This blue line labeled caught may be interpreted as the time axis for the second observer. Together with the path axis, it represents his coordinate system. Both observers agree on the location of the origin of their coordinate systems. The axes for the moving observer are not perpendicular to each other, and the scale on his time axis is stretched. To determine the coordinates of a certain event, two lines, each parallel to one of the two axes, must be constructed passing through the event, and their intersections with the axes read off. Determining position and time of the event A as an example in the diagram leads to the same time for both observers, as expected. Only for the position different values result, because the moving observer has approached the position of the event A since t equals 0. Generally stated, all events on a line parallel to the path axis happen simultaneously for both observers. There is only one universal time t equals t, which corresponds with the existence of only one common path axis. On the other hand, due to two different time axes, the observers usually measure different path coordinates for the same event. This graphical translation from x and t to x and t, and vice versa, is described mathematically by the so-called Galilean transformation. Minkowski diagram in special relativity. Albert Einstein discovered that the Newtonian description is not correct, with Hermann Minkowski providing the graphical representation. Space and time have properties which lead to different rules for the translation of coordinates in case of moving observers. In particular, events which are estimated to happen simultaneously from the viewpoint of one observer, happen at different times for the other. In the Minkovski diagram, this relativity of simultaneity corresponds with the introduction of a separate path axis for the moving observer. Following the rule described above, each observer interprets all events on a line parallel to his path axis as simultaneous. The sequence of events from the viewpoint of an observer can be illustrated graphically by shifting this line in the diagram from bottom to top. If court instead of t is assigned on the time axis, the angle alpha between both path axes will be identical with that between both time axes. This follows from the second postulate of the special relativity, saying that the speed of light is the same for all observers, regardless of their relative motion. Alpha is given by the corresponding translation from x and t to x and t, and vice versa is described mathematically by the so-called Lorentz Transformation. Whatever space and time axes arise through such transformation. In a Minkowski diagram, they correspond to conjugate diameters of a pair of hyperbolas. The scales on the axes are given as follows. If u is the unit length on the axis of court and x respectively, the unit length on the axis of court and x is. The court axis represents the world linear of a clock resting in S, with u representing the duration between two events happening on this world linear, also called the proper time between these events. Length u upon the x-axis represents the rest length or proper length of a rod resting in S. The same interpretation can also be applied to distance u upon the court and x-axis for clocks and rods resting in S. History. In Minkovski's 1908 paper there were three diagrams, first to illustrate the Lorentz transformation, then the partition of the plane by the light cone, and finally illustration of world lines. The first diagram used a branch of the unit hyperbola to show the locus of a unit of proper time depending on velocity, thus illustrating time dilation. The second diagram showed the conjugate hyperbola to calibrate space, where a similar stretching leaves the impression of Fitzgerald contraction. In 1914, Ludwig Silberstein included a diagram of Minkowski's representation of the Lorentz transformation. This diagram included the unit hyperbola, its conjugate, and a pair of conjugate diameters. Since the 1960s, a version of this more complete configuration has been referred to as the Minkowski diagram, and used as a standard illustration of the transformation geometry of special relativity. E.T. Whittaker has pointed out that the principle of relativity is tantamount to the arbitrariness of what hyperbola radius is selected for time in the Minkowski diagram. In 1912, Gilbert N. Lewis and Edwin B. Wilson applied the methods of synthetic geometry to develop the properties of the non-Euclidean plane that has Minkowski diagrams. Lodal diagram. While the rest frame has space and time axes at right angles, the moving frame has primed axes which form an acute angle. Since the frames are meant to be equivalent, the asymmetry may be disturbing. However, several authors showed that there is a frame of reference between the resting and moving ones where their symmetry would be apparent. In this frame, the two other frames are moving in opposite directions with equal speed. Using such coordinates makes the units of length and time the same for both axes. If n is given between S and S, then these expressions are connected with the values in their median frame as follows. For instance, if between S and S, then by they are moving in their median frame with approximately plus or minus 0.268 c each in opposite directions. On the other hand, if in, then by the relative velocity between S and S, in their own rest frames is 0.8 c. The construction of the axes of S and S is done in accordance with the ordinary method using with respect to the orthogonal axes of the median frame. However, it turns out that, when drawing such a symmetric diagram, it is possible to derive the diagram's relations even without mentioning the median frame at all. Instead, the relative velocity between S and S can directly be used in the following construction, providing the same result. If is the angle between the axes of court and between the axes of x and court, it is given. Two methods of construction are obvious from Fig. 2. The x-axis is drawn perpendicular to the court axis. The x and court axes are added at angle. The x-axis is drawn at angle with respect to the court axis. The x-axis is added perpendicular to the court axis and the court axis perpendicular to the x-axis. Also, the components of a vector can be vividly demonstrated by such diagrams. The parallel projections of vector are its contravariant components, its covariant components. History: Max Born drew Minkovski diagrams by placing the court axis almost perpendicular to the x-axis, as well as the court axis to the x-axis, in order to demonstrate length contraction and time dilation in the symmetric case of two rods and two clocks moving in opposite direction. Dmitry Mirimanoff showed that there is always a median frame with respect to two relatively moving frames, and derived the relations between them from the Lorentz Transformation. However, he didn't give a graphical representation in a diagram. Symmetric diagrams were systematically developed by Paul Gruner in collaboration with Joseph Sauter in two papers in 1921. Relativistic effects such as length contraction and time dilation and some relations to covariant and contravariant vectors were demonstrated by them. Gruner extended this method in subsequent papers, and gave credit to Mirimanoff's treatment as well. The construction of symmetric Minkovski diagrams was later independently rediscovered by several authors. For instance, starting in 1948, Enrique Lodel Palumbo published a series of papers in Spanish language, presenting the details of such an approach. In 1955, Henry Amar also published a paper presenting such relations, and gave credit to Lodel in a subsequent paper in 1957. Some authors of textbooks use symmetric Minkowski diagrams, denoting as Lodel diagrams. Time dilation. Relativistic time dilation means that a clock that moves relative to an observer is observed to run slower. In fact, time itself in the frame of the moving clock is observed to run slower. This can be read immediately from the adjoining Lodel diagram quite straightforwardly because unit lengths in the two system of axes are identical. Thus, in order to compare reading between the two systems, we can simply compare lengths as they appear on the page. We do not need to consider the fact that unit lengths on each axis are warped by the factor, which we would have to account for in the corresponding Minkowski diagram. The observer whose reference frame is given by the black axis is assumed to move from the origin O towards A. The moving clock has the reference frame given by the blue axis and moves from O to B. For the black observer, all events happening simultaneously with the event at A are located on a straight line parallel to its space axis. This line passes through A and B, so A and B are simultaneous from the reference frame of the observer with black axis. However, the clock that is moving relative to the black observer marks off time along the blue time axis. This is represented by the distance from O to B. Therefore, the observer at A with the black axis notices his or her clock as reading the distance from O to A while he or she observes the clock moving relative him or her to read the distance from O to B. Due to the distance from O to B being smaller than the distance from O to A, he or she concludes that the time passed on the clock moving relative to him or her is smaller than that passed on his or her own clock. A second observer, having moved together with the clock from O to B, will argue that the other clock has reached only C until this moment and therefore this clock runs slower. The reason for these apparently paradoxical statements is the different determination of the events happening synchronously at different locations. Due to the principle of relativity, the question of who is right has no answer and does not make sense. Length contraction. Relativistic length contraction means that the proper length of an object moving relative to an observer is decreased, and finally also the space itself is contracted in this system. The observer is assumed again to move along the court axis. The world lines of the endpoints of an object moving relative to him are assumed to move along the court axis and the parallel line passing through A and B. For this observer, the endpoints of the object at T equals 0, O and A. For a second observer moving together with the object, so that for him the object is at rest, it has the proper length ob at T equals 0. Due to OA less than ob, the object is contracted for the first observer. The second observer will argue that the first observer has evaluated the endpoints of the object at O and A respectively and therefore at different times, leading to a wrong result due to his motion in the meantime. If the second observer investigates the length of another object with endpoints moving along the court axis and a parallel line passing through C and D, he concludes the same way this object to be contracted from OD to OC. Each observer estimates objects moving with the other observer to be contracted. For all these considerations, it was assumed that both observers take into account the speed of light and the distance to all events they see in order to determine the actual times at which these events happen from their point of view. Constancy of the speed of light. Another postulate of special relativity is the constancy of the speed of light. It says that any observer in an inertial reference frame measuring the vacuum speed of light relative to himself obtains the same value regardless of his own motion and that of the light source. This statement seems to be paradoxical, but it follows immediately from the differential equation yielding this, and the Minkovski diagram agrees. It explains also the result of the Michelson-Morley experiment, which was considered to be a mystery before the theory of relativity was discovered, when photons were thought to be waves through an undetectable medium. For world lines of photons passing the origin in different directions, x equals court and x equals minus court holds. That means any position on such a world line corresponds with steps on x and court axis of equal absolute value. From the rule for reading off coordinates in coordinate system with tilted axes follows that the two world lines are the angle bisectors of the x and court axis. The Minkovski diagram shows that there are angle bisectors of the x and court axis as well. That means both observers measure the same speed c for both photons. Further coordinate systems corresponding to observers with arbitrary velocities can be added to this Minkovski diagram. For all these systems, both photon world lines represent the angle bisectors of the axes. The more the relative speed approaches the speed of light, the more the axes approach the corresponding angle bisector. The path axis is always more flat and the time axis more steep than the photon world lines. The scales on both axes are always identical, but usually different from those of the other coordinate systems. Speed of light and causality. Straight lines passing the origin which are steeper than both photon world lines correspond with objects moving more slowly than the speed of light. If this applies to an object, then it applies from the viewpoint of all observers. Because the world lines of these photons are the angle bisectors for any inertial reference frame. Therefore, any point above the origin and between the world lines of both photons can be reached with a speed smaller than that of the light and can have a cause-effect relationship with the origin. This area is the absolute future, because any event there happens later compared to the event represented by the origin regardless of the observer, which is obvious graphically from the Minkovski diagram. Following the same argument, the range below the origin and between the photon world lines is the absolute past relative to the origin. Any event there belongs definitely to the past and can be the cause of an effect at the origin. The relationship between any such pairs of events is called time-like, because they have a time distance greater than 0 for all observers. A straight line connecting these two events is always the time axis of a possible observer for whom they happen at the same place. Two events which can be connected just with the speed of light are called light-like. In principle, a further dimension of space can be added to the Minkovski diagram, leading to a three-dimensional representation. In this case, the ranges of future and past become cones with apexes touching each other at the origin. They are called light cones.